India ranked 1. Then he joined IISc, and again he was topper here, and he published in Fox and Soda during his from his work here during his MTech. And after that, he went to MIT for PhD with David Karger, and following that, he has done a lot of influential and breakthrough work in graph algorithms and algorithms under uncertainty. And today he will talk about all pairs minimum cuts in nearly quadratic time, a breakthrough result again.
Okay, so thank you very much, Arsham. That was a very generous introduction. And it's great to be back here. So as some of you know, I was a student here many years ago. All right, so I'm going to be talking about this problem called all pairs minimum cuts, and please stop me anytime. It's should be an interactive session rather than and this is joint work with a lot of excellent colleagues, one of whom we are going to hear from later in the day. Amira Booth from Weizmann, but also Roby Taylor, also from Weizmann, Mohat Trabelsi from TTI Chicago, Jason Lee from the Science Institute, and Achapal Sir from University. All right, so in this talk, before I even introduce the problem, it's worth saying that what we are going to be talking about are undirected graphs. So the graphs of the third kind shown at the bottom are not going to be part of this stuff. There are no directions on the edges. But what I'm going to allow are weights on the edges, and these weights I'm going to assume are polynomially bounded in the size of the graph. This assumption is not critical. You can remove the assumption. For the purpose of this talk, it's a little cleaner if I remove it. Okay, so that's the kind of graph that I will be dealing with. Now, in a graph, a cut is just a set of edges whose removal disconnects the graph. So you can either think of that as the edges that which when removed create two components, or you can just think of it as this bipartition itself that's produced by these two entities. And the minimum ST cut, this is going to be sort of a central player in our talk today, is a minimum weight cut that separates two given vertices S and T in the graph. So among all the cuts which separate S and T, which have S and T on two different sides, a minimum ST cut is one that has minimum. Of course, it need not be unique. There can be many minimum. Here's an example. So I have a graph. I have some edge weights. If I chose the two vertices I've shown as S and T, then the minimum ST cut is actually just a degree cut around there. And that has weight 2 in this case. I want to distinguish it from another kind of min cut that some of you might have encountered, which is a global minimum cut. That's just a minimum among all cuts in the graph. There's no constraint on separating a particular pair of vertices. And in this graph, for example, the global min cut is different from the minimum ST. So in some cases, S and T may be on the same side of the global min cut, in which case the identity of the minimum ST cut could be different from that of the global min cut. And the particular problem I'm going to be interested in today is the all pairs min cuts problem. So instead of trying to find the minimum cut separating one particular pair S and T, I want to report minimum cuts for all pairs of vertices. So if you iterate over all the and choose two pairs of vertices, each of them has a minimum ST cut. I want to report all of them rather than just one pair. So if you are familiar with shortest path problems, think of this as the minimum cut version of all pair shortest paths. Now, if you see this problem, maybe the first thing you think about is the Maxwell min cut theorem. This is a classic theorem that says that the value of an ST Maxwell for any given pair of vertices S and T is exactly equal to the value of an ST min cut. This is one of the classic examples of ST min. And therefore, an ST min cut, in fact, can be recovered from any Maxwell algorithm. So if I give you the maximum flow between S and T, it's very easy to recover the minimum ST cut from that. So that gives you an algorithm for solving the problem of all pairs min cut or all pairs Maxwell, which is just run ST Maxwell for all pairs of vertices. That's the naive algorithm. There n choose two vertices, so it takes time, the n squared times the running time of your Maxwell algorithm. Yeah, and of course, the algorithm itself, the overall algorithm, is agnostic of what specific Maxwell algorithm is. Any algorithm will work. Okay. All right. So that's where we start. Now, 60 years ago, in one of the most remarkable early results in graph algorithms, Gomory and Hu showed that you can do something much better. So what they did was they defined a tree called a cut tree, or later also called a Gomory-Hu tree, on the same set of vertices as a graph. So I gave you an undirected graph. Gomory and Hu would give me back a tree on the same set of vertices. This tree will be a weighted tree, irrespective of whether the graph is weighted or unweighted. Okay? So I give you some graph which could be weighted or unweighted. What Gomory and Hu give me back is a tree on the same set of vertices. And the tree has the following property. So if you take any pair of vertices S and T in the graph, then of course on the tree, the minimum ST cut is simply the minimum weight edge on the ST path. The tree has a unique ST path, and the minimum cut separating S and T would be the edge with the minimum weight on this ST path. Right? So if I want to separate S and T on a tree, I need to take out one of the edges on the path connecting S and T. Which edge would be the one that I should take out if I want to find the min cut? The one that has minimum weight. So for any pair S and T, there is a minimum weight edge in the tree. Now that minimum weight edge, if I remove this, then the set of vertices splits into two sets. Right? That's the minimum ST cut of the tree. Let me take those two sets and superpose those on the graph that I was given. So that particular bipartition of vertices is also a ST cut in the graph. Remember, the graph and the tree are on the same set of vertices. Now, the property of a Gomory-Hu tree is that this cut that you get in the graph is going to be a minimum ST cut of the graph. And the weight of this cut is going to be exactly equal to the weight of that edge, the minimum weight edge that you remove. Okay, so minimum ST cut on the tree corresponds to a minimum ST cut on the graph. And this property simultaneously holds for every pair of vertices S and T. So the tree encodes minimum ST cuts for all pairs of vertices S and T in the graph. And if I actually gave you a particular pair, it's very easy to recover in log n time the minimum ST cut from the tree itself. Okay, so then the next question is, okay, so this seems an interesting data structure. Question is, how can I construct this? So Gomory and Hu also, yes.
This also interestingly points out that even if I look at all 10 choose 2 vertices, the number of min cuts is actually
not number of min cuts, but the number of different values of min cuts is only n minus 1. That's right. Okay. So now, how do you construct a Gomory-Hu tree? And that will be the central object of study today. So we'll basically be looking at algorithms that construct a Gomory-Hu tree. So Gomory and Hu suggested the following algorithm. So you take your graph, you choose any pair of vertices S and T, any arbitrary pair, run a Maxwell algorithm, find the minimum ST cut for that particular pair that you chose. Okay. Then you go to the next phase where you contract each side of the graph and create two separate graphs. So G sub S is this graph where I contracted the vertices in T. The vertices in S are not contracted. On the other hand, I've constructed a second graph, which is G sub T, where I've contracted all the vertices in S into a single vertex. The vertices in T are uncontracted. Okay? So you create these two different graphs and you recurse. Okay? So now once you recurse on these two graphs, you produce inductively Gomory-Hu trees for these two graphs. Of course, each of these graphs individually does not contain all the vertices. Some of the vertices have gotten contracted. So now, in the last step, I need to take the Gomory-Hu trees that I constructed in these two graphs individually, G sub S and G sub T, and somehow stitch them back into a single Gomory-Hu tree for the entire graph. How do we do this? So the useful property is that both of these Gomory-Hu trees, the one coming from G sub S and the one coming from G sub T, share this one common edge. Here it's an edge of weight 2 that corresponds to this first cut that I have started with. So this cut remains a minimum cut in both of the graphs. So this cut shows up in both of these Gomory-Hu trees. Yeah, and they have this common edge too. So now you merge them in the most natural way you can think of merging, just unify this edge. You can also think of taking any one of the trees and using the other tree to expand out the contracted vertex. And what you get, they show is the correct Gomory-Hu tree for the overall graph. Okay. So that's the basic algorithm that they, or at least the second algorithm after the naive baseline. Yes.
The order in which you construct the edges, does it matter? Is it a unique tree?
No, it's not a unique tree. The order does not matter. You can start with any pair of vertices. Yeah.
Which vertex on the non-contracted component are you going to connect here?
Which edge?
So we have one edge which is the
Yes.
weight will be the SD. But so
Just think of taking the two and merging it at that end.
not going to be one edge in the original graph, right? It would be a set of edges.
Yes. You're not worried about the original graph at this point.
So when you do the merging, where are you going to which vertex is this edge going to be at?
Exactly the one given by your trees. So for example, here, this edge is adjacent to T there and the vertex above 4 here. So when you merge the edge, those would be the two endpoints of the edge. In both copies, one of the endpoints is the real vertex. So those two would be the endpoints. Okay?
This would work even in the weighted case.
Yes, this works even in the weighted case. Any other questions?
Ideally, you'd like to find cuts that such that both S and T have roughly half the.
That's right. So we'll get to that. Yeah, that would be a nice thing to do. Okay, so now if you think about what's going on in this algorithm, really what's going on is that in each step of this recursive process, you're running an ST Maxwell algorithm, and that's revealing one edge of a Gomory and Hu tree. Right? So the first step of my algorithm ran this ST Maxwell and revealed this one cut of weight 2. Okay? So really, overall, in the entire recursive algorithm, we will end up running ST Maxwell calls n-1 times because each call reveals a new edge in the tree. So the overall running time of this algorithm is theta of n times the running time of Maxwell. So remember the naive algorithm was theta of n squared times the running time of Maxwell. Now we have gotten it down to theta of n times the running time. Okay, so that was the state of the art in 1961, and turns out that's still the state of the art. So let's see what people have been doing for these 60 years. So one of the first algorithms that, one of the first sort of distinct algorithms for this problem was given by Gusby, who gave an algorithm that in some ways is a variation of Gomory and Hu's algorithm. And there are certain advantages of Gusby's algorithm, but in the worst case, it has exactly the same running time. It also takes theta of n Maxwell. So the asymptotic running time did not issue. And then there has been a long line of work that improves, that gets better running time, gets faster algorithm for various special cases of the problem. One of the first was something I did when I was a student here, a long time back. So this was work with Anand Halgat, Ramesh Hariharan, and Kavita. What we did was we looked at unweighted graphs. Okay? So our result does not apply to general graphs. Just works on unweighted graphs, and we gave an algorithm that runs in time that's about m times n, m being the number of edges, n being the number of vertices. Okay? And I'll be using this notation O tilde in various places. That just means that I'm suppressing polylog factors. I'll not bother with the precise polylog factors. So that was an improvement after a long time. And then Carter and Levi, they already had an existing algorithm using some combinatorial properties that we showed in our paper. They showed that their existing algorithm also runs has the same running time, also on tilde. So there were these two algorithms that got the running time down to m times n from n Maxwells. And then Amir, who you are going to be hearing from later in the day, he had a couple of papers with Krausgammer and Traversy. All three are co-authors on this paper. They first showed that you can replace the n in our running time by a square root of n. So square root of the number of edges is always at least as good as the number of vertices. The total number of edges cannot exceed n squared. So they replaced n by square root of n. They slightly lost in the subpolynomial term. So earlier we used to have logarithms. They now had something that is subpolynomial but not quite a logarithm. And then they showed that you can do even better. So you, instead of getting n Maxwells, which was what Gomory and Hu and Gusby did, they showed that you can now solve the problem using square root of n Maxwells. But of course, this was specific to unweighted graphs, whereas the Gomory, Hu, and Gusby algorithm also applies to it. So that was about unweighted graphs, and then we went even sort of narrower, and we looked at simple graphs. So in the first three papers and the first three bullets in this block are papers that came out essentially simultaneously. This was concurrent work, and all three of them, I was involved in one of them. Abu programmer at Traversity had one, and then there was an independent paper by Hu. All three of them basically got the same result. All three of them showed that if you restrict it further to simple graphs don't allow parallel edges. So if you restrict it further to simple graphs, then you can even go further, and you can get algorithms that run n squared time, roughly n squared time. Yeah, and n squared, of course, is better than square root of n Maxwell, because if your graph is dense, it has n squared edges. A single Maxwell call will take at least n squared time. So square root n Maxwell is at least n to the 2.5 if the graph is dense. Okay, and then in a later work, Abu programmer and Traversity again showed that indeed, in fact, this is not the best you can do. You can go further. So they improved this running time slightly to n to the 1.9, but this was a proof of concept that n squared wasn't the right bound. You can go further. So that was the story with simple graphs. And then there are other ways that you can relax the problem. For instance, one way to relax the problem is to allow approximations. So now if I say that I only want like I don't care about getting exact ST cuts. If I'm happy to take a hit in the approximation, let's say I want only 1 plus epsilon approximate ST cuts, then we had an algorithm, me with Jason Lee, we had an algorithm that actually solves this in the best thing you can hope for, which is polynomial Maxwell calls. Okay, so remember the transition was n squared for the naive algorithm, then n for Gomory, Hu, and Gusfield, square root n in the above programmer Traversity for unweighted graphs. And this one is saying that you can actually handle weights, but then you need to allow approximations, and then you can get actually polynomial Maxwell calls. Of course, having a Maxwell call is a basic bottleneck, right? Because I'm finding all pairs min cuts, even one pair min cut is Maxwell. So you can't go below the running time of Maxwell. And this is saying that if you take only an overhead of a polylog factor, then you can actually find all pairs, but only up to a 1 plus epsilon.
Yes. The number of Maxwell calls depend on epsilon.
Yes. So the number of calls is polylog n with some function of epsilon, some polynomial in one of them. I'm assuming epsilon is a constant. So.
Exactly. Why simple graph it was easy to do, not easy, but it was not easily extendable to general graphs.
Oh, why is simple graph not extendable? We'll see some reasons soon. There are lots of reasons. Like the algorithm that I'm going to present for general graphs is has pretty much nothing to do with the algorithm. Okay, and then of course all of these are for general graphs. If you restrict the graphs in some other manner, in some kind of structural way, so for example, if you focus on planar graphs, or surface embeddable graphs, or bounded treated graphs, and things like this, there are many other examples, then this all pairs Maxwell problem has very fast algorithm for all of them. So I think the planar graphs algorithm came out in like Fox 13, surface embeddable was Fox 14. So in the last 10 years, all of these very special cases of graphs that people care about, all of these have actually. But the bottom line, as I started off in the slide, yeah.
Quick clarification. So when we say like these many Maxwell calls, it's probably with the same, not necessarily the same graph, but graphs with the same number of vertices or something.
Yeah. So I'm cheating slightly. So when I say this many Maxwell calls, what I mean is that the running time of all the Maxwell calls that I am running is equal to this number, whatever polylog n or whatever I'm saying, times a single Maxwell call in the entire graph. But the actual Maxwell calls can sometimes run on small parts of the graph and be much faster.
Yeah, so somehow, yeah, the primitive of using Maxwell calls as your unit is just motivated by the observation that you mentioned, that even for a single pair you do.
That's right, and also the fact that the use of Maxwell is black box completely. It's not that I need to go in and like search for the right Maxwell algorithm.
Recent should take to.
Yeah, all of those apply.
These are both for all pairs Maxwell and all pairs Maxwell.
So depends on what you mean by that. So traditionally, all pairs, of course, for all pairs min-cut, yes. For all pairs Maxwell, traditionally, what that means is that you get all pairs Maxwell value, and for that, yes. If you actually wanted the flow, that representation size is already. Any other questions? Yes.
So when you said polygon Maxwell, it's not actually polygon calls to Maxwell, it would be more, just that the total runtime is polygon times the Maxwell on the entire way.
That's right. And but in a black box sense. Any Maxwell algorithm would have that property. Other questions? Okay, so we didn't have an improvement to this 60-year-old algorithm. In the meantime, of course, Gomory and Hu trees and these all pairs Maxwell min-cut problems have become part of textbooks and survey articles have been written and have been applied to a variety of different domains, including networks, image processing. Okay, so let's look at this question of trying to get a better algorithm for this problem from a different lens now. So recall that Gomory and Hu's algorithm uses about n Maxwell calls, and at best this gives an n cube time algorithm because, as I said, your graph can have n squared edges. So no Maxwell algorithm can run in better than n squared time on a graph that has n squared edges. So in that case, this kind of an algorithm, you cannot hope to have a running time that's better than n. And this is a fundamental barrier in the sense that this is something that's not contingent on whether we have the right Maxwell algorithms or not. This is saying that even if we had the best Maxwell algorithms in the world, which we may not have at the moment, even if we had that, this barrier remains. Okay, so one way of stating the question that I on the previous slide is whether we can break this cubic barrier of the all-pair Maxwell problem. Now, when you see a cubic barrier, one of the things that reminds you of is the shortest path problem or the all-pair shortest path problem. So in fact, there's the same cubic barrier for weighted graphs in all-pair shortest path, and this is in fact one of the foundational assumptions or foundational conjectures of FGC, of fine-grained complexity. I think you're going to hear a lot about fine-grained complexity later today. So in fine-grained complexity, people believe that you cannot solve all-pair shortest path in weighted graphs better than n cube time, or at least significantly better than n cube time. Okay, and similar to all pairs max flows, if you relax the problem in some manner, so for example, if you went to unweighted graphs and asked all-pair shortest paths, then you can solve it much faster. You can use things like matrix computation. If you went to if you allowed approximation on the paths, you didn't care about exact shortest paths, again, you can solve it a lot faster. So there are these sort of superficial similarities, which kind of makes you question, is it really not feasible to solve all pairs max flow faster than n cube time? Or one other way of putting it is all pairs max flow really easier than all pairs shortest path? And this seems, I mean, the first hunch would be that it's not, because if you think of a single pair, then max flow has been a really difficult problem. We have studied it over 60 years, and only now we are starting to get algorithms that get close to linear time. If you think of shortest path for a single pair, there's a trivial algorithm that gets linear time, Dijkstra's algorithm. Right? So in one case, you have a trivial algorithm. In the other case, you really have to work hard for 60 years to get a linear time algorithm. So there is some school of thought that believed that max flows in general are harder problems, and all pairs max flow is a harder problem than all pairs shortest path. And in fact, there were a group of people in fine-grained complexity that tried to use this to prove formally that all pairs max flow also has this n cube barrier. So if you could reduce shortest paths to all pairs shortest paths to all pairs max flow, then you could use this fine-grained complexity conjecture that APSP doesn't have a better than n cube time algorithm to say that APNF doesn't have one algorithm. Okay. So that they of course didn't succeed. That's why I'm standing here and giving you a talk. But that was a basic question that also drove this research in the last 5 to 7 years.
hindsight,
Yeah.
this is completely in hindsight. But the output itself in the case of all pair maximum flow is a much more succinct list versus all pair short.
That's right. So you're right. So, but all pair shortest path output is n squared. So,
Yeah.
I mean, n squared versus an n cubed barrier is not completely clear. I mean, of course, there's an n squared barrier, but we are talking about an n cubed barrier here. And the other thing is that's true for weighted graphs. If you go to unweighted graphs, again, all pair shortest path only has -1 answers. So. Other questions?
Has there been other approaches to the all-pair maximum other than the Gomory and Hu?
No, so it's formed like there's a proof showing that no matter what algorithm you use to find all pairs maximum can be converted into linear time in a Gomory transition. So focusing on a Gomory tree is without any loss. Other questions? Okay. Okay, so here's our result. So we give a Monte Carlo algorithm. So Monte Carlo algorithms, if you're not familiar with them, are these algorithms that are randomized, and with some small tiny probability, they will sometimes give you a wrong answer, but you won't know when they're giving you a wrong answer. So it's a randomized Monte Carlo algorithm for constructing a Gomory tree, and therefore these all pairs minimum cut and max flow problems. And this runs in time that's about n squared. It's n squared times some polynomial factors. Works on any weighted graphs. We are going to assume that the weights are polynomially bounded. If they're not polynomially bounded, there's some logarithmic dependence on the aspect ratio of the weights, like the max to minimum weight ratio. But the polynomial bound is not a crucial property of the algorithm. Okay, so that's the result. Now this gives the first improvement, as I said, over Gomory and Hu's algorithm, breaks the cubic barrier, the n square time algorithm. It implies that either the APSP conjecture is false, so either APSP can be solved in better than cube time, significantly better, and that would falsify many results in FGC, or APMF is actually easier than APSP, which seems the more likely possibility at this point, but didn't seem intuitive 5 years back. And our result is independent of the new Maxwell algorithm. So we get n squared time, even if we go back and use existing Maxwell algorithm from 2 years back. So there is a new breakthrough Maxwell algorithm that runs in time that's almost linear, but we don't need this published result. And finally, we also give an algorithm in unweighted graphs for the same problem for Gomory tree that only uses sub-polynomial Maxwell calls. So it's using this new Maxwell algorithm, that's an almost linear time algorithm for Gomory. So that means that in unweighted graphs, all pairs max flow is the same as a single max flow. In weighted graphs, that's the case for dense graphs that has n squared edges. For sparser graphs, we are still a bit off. Okay, the Maxwell algorithm still runs in linear time, our algorithm runs in n-squared. Questions about the results? Yes.
APSP conjecture is used for any algorithm or deterministic algorithm or randomized Monte Carlo also?
Yeah, all algorithms. It's definitely combinatorial algorithm. I think maybe also for computer. Any other questions? Okay. Yes.
Result is independent of the recently discovered algorithm. So what does it exactly mean?
So even if you plug, so our results will use Maxwell as a black box. In that black box, if you plug in slower Maxwell algorithms that already existed before this recent Maxwell algorithm, you still get the same result.
But that might make your algorithm more efficient also. Use this black box.
Actually not. So even if you use this particular new algorithm, there's a different place where there's an n-squared model. So it's still be n-squared. But worst case running time will be. Yes.
Can it be made off or would it time?
The Gomory tree? Yes, and it certainly is possible, and I'll say a few words about that at the end. But not the algorithm today. The one I'm presenting today. Yes.
When we say that the weights are polynomially bound, suppose the number of vertices and the weight of an entity required
So I mean, okay, so it can be 2 to the n, but then the minimum weight needs to be 2 to the n divided by a polynomial. So when I say it's polynomially bounded, I mean that the ratio between the maximum to minimum weight is some polynomial in the size of the graph. I mean, if all your weights are exponential, I mean, you can just scale the whole thing down by the minimum weight. So you can always assume that your minimum weight is weight 1, in which case this assumption says maximum weight is some polynomial.
It's kind of pseudo polynomial. Because minimum weight is 1 and the maximum weight is 1.
Then you will get hit with an extra factor of n in the algorithm, because in general you will get hit with a factor of log of the ratio of the maximum to minimum weight. So if that ratio is exponential, then naively you will get hit with an exponential factor.
So this log W naught by W min dependence can be removed or it's necessary?
The kind of algorithm that I'm going to describe is necessary. It's plausible that it can be removed, but I don't know how, and I'm also a lot of the results that I stated on that big slide of results also have exactly the same dependence. So if you don't allow that, then you will probably go back almost to Gomory and Hu 3, or like the Gomory and Hu algorithm or something. So all these like unweighted, all these like special cases then are this that I mean many of them have the same. Also this approximate.
So what is the final verdict on the second point? Is it either or both?
Yeah, so no, I mean one of the two must be true. And the first one, of course, no one has falsified the conjecture. The second one is a sort of a qualitative statement. So given that no one has falsified the conjecture, I mean you can at best go with the qualitative statement.
But it's possible both of them might turn out.
Yes, that's possible.
The IISc conjecture for polynomially bounded weights?
Yes.
Can you just speak more to the difference about the difference between APNF and APST? What's the fundamental?
I mean the similarities are superficial. There's like, in terms of the combinatorial structure, there is no like they are different from very completely different. Yes. For unweighted graphs, they are better than include algorithm. Other questions? Okay, let's move on. Okay, so let's go back to the Gomory and Hu algorithm and let's try and understand where this algorithm is doing. So what is the Gomory and Hu algorithm doing? It starts with some graph G, then it creates these two subproblems where you find a minimum cut, ST min cut in G, and then you create two subproblems with two graphs G sub S and G sub T. And then of course you recurse, so G sub T will again split into two subproblems, G sub S will split into two subproblems, etc. Now, if you look at this recursion tree, you can think of this recursion tree as these various layers of graphs. Right? Each layer consists of a bunch of different graphs. So if you think of the first layer, what's happening? You have sort of one expanded side in GT, the other side expanded in G sub S, and the interface exists in both of these graphs. So modulo this interface, for a second, ignore the interface. Modulo this interface, every edge appears in either G sub T or G sub S. It doesn't appear in both. Right? Of course, the edges in the interface appear in both. But modulo that, every edge appears in one of the two. So if you keep ignoring the interfaces, then every layer consists of a bunch of graphs cumulatively containing every edge of the original graph once. It's just that the edges at the interface gets repeated multiple times. Now, if you were dealing with unweighted graphs, then it is formally easy to show that the total weight of the edges in the interface, the total number of times these get repeated, is no more than the total size of the graph, or maybe constant times the number of edges in the graph. So in unweighted graphs, in every layer of this recursion tree, the total number of edges you're dealing with across all these graphs is some constant times the number of edges that you started with. Okay. In weighted graphs, this is not precisely correct, but you can sort of simulate this property, and for intuitive purposes, it's good to keep this property in mind. Okay, so for now, just imagine that you have a situation where for each layer of this recursion tree, the set of subproblems, the set of graphs that I am given, add up to just the number of edges of the original graph, maybe times some constant. So if we had this, now what am I doing? Now in each of these graphs, I'm running some Maxwell algorithms. So if I had the property that the total number of edges in each of these layers is O of n, then clearly all these Maxwell calls across these subproblems only cost me the same as one Maxwell call, or maybe constant many Maxwell calls. So if the depth of my tree were d, then automatically Gomory Hu's algorithm would take or have a running time of d times, or maybe order d times the Maxwell calls. Okay? So if the depth is small, we are actually in very good shape. If the depth were just log n, for instance, then we would actually have an algorithm that runs in log n Maxwell calls. And as Siddharth was saying, if your splits were nice, right? If you always had half the vertices going in each of the two subproblems, then indeed you will have a depth of log n, right? Because you're losing a constant factor in your going up.
This also inspires the polynomial method to do some sort of isolation lemma, perturb the values of the data.
Oh, for approximations?
Yeah.
Yes, but it doesn't quite work, because what happens is that the approximation factor increases. The approximation error keeps increasing as you go down. So you need to be a little careful about that. Yes.
By constructing this Gomory Hu tree, we can make sure that tree looks like any tree we want.
I mean, the Gomory Hu tree is not unique, but it's not that I can give you a tree and you can fill in weights and get a Gomory Hu tree.
Like this tree can also be constructed, right? On the like we just take one.
Not necessarily. Like depends on the particular problem. Like depends on the particular job.
This actually is the recursion tree of the Gomory
Yeah.
Yeah.
And as that says, this is the recursion tree of the algorithm, not the actual.
That the sum of all the Maxwell calls is no more than the sum of Maxwell call of the entire graph.
Yes.
This is true for any black box Maxwell, and I suppose use the property that you need to at least spend a linear time on the Maxwell.
Yes, exactly.
Breakdown.
Yes. Because it's a polynomial with a degree higher than. Okay. Now the problem, of course, is that your recursion tree may not look like this. It may not be balanced. It might look like what I have drawn on the right. Right? You might be splitting out one vertex at a time. So you go from n vertices to n minus 1 to n minus 2, etc. And your depth is actually n. And this is actually it's easy to construct an example where this will happen. If your graph were just a star, then what will happen is that each leaf of the star will get cut off in each of these runs, and you will actually end up with this very deep tree. So the basic idea in many of these early works in trying to improve this running time was to somehow restrict the depth of the Gomory Hu tree. If we could do some massaging of the graph, something to try and restrict the depth of the Gomory Hu tree, then we would automatically be able to use the Gomory Hu algorithm on this, and we would get a better algorithm. Unfortunately, I don't know how to reduce the depth of the question. Okay. Yes.
This target you gain in the it's past graph, for example. Yeah. You gain the other side, or?
Well, I mean, you would have a depth of n, so you would end up with n max flows because you have n layers. I mean, it is a sparse graph, so max flows individually are fast, but it's still n max flows. Okay, so instead of trying to, one of our sort of basic
Start graphs,
yes.
like the quintessential property is actually that you don't want linkers that have degree cuts.
Yes. I mean, okay, yes. Yes.
That's sort of the worst case in a.
Yes. You want to somehow be able to identify a lot of these cuts together instead of doing this one at a time, because basically you are running your max flow over the same graph over and over again. Okay. So the first thing we do is, so as I said, we don't know how to reduce the depth of this tree. Instead, we replace Maxflow by a more powerful gadget. So we replace Maxflow by a single source min cut gadget, and I'll tell you what this is. So remember, Maxflow is a single pair min cut gadget, right? I give you a pair S and T. You want to find the minimum cut between S and T. Now, what's a single source min cut problem? It says that I'll only give you one vertex S, and you have to find me ST min cuts for all vertices T in the graph other than S. Okay, so iterate over all the other vertices and find me ST min cuts for all of them. So this sits somewhere in between the all pairs problem and the single pair problem. Single pair says it's one pair, all pairs says it's n choose two pairs, single source says it's n minus one pairs. Okay? So we'll replace Maxflow by this much more powerful gadget, and let's see why that helps. So let's say this is your Gomory Hu tree. Okay, so I'm sorry the trees are faded out a little bit in the background, but the tree that you can see, let's say that's your Gomory Hu tree. Ignore the stuff on the right for now. Now let's say I chose this vertex S at the bottom as my source. So now from this vantage point, I'm trying to find minimum cuts for all the vertices in the graph, right? So if you look at the minimum cuts for the two vertices on the two sides of S, they would just correspond to the edge from S to that vertex. There's in fact just one cut in the Gomory Hu tree. Now if you look at the vertices on top, then the four vertices in the cluster on the top left, their internal edges will not be revealed by a single source min cut from S. Because for all of those four vertices, their minimum cut from S is actually this edge of weight 2. Right? That's an edge of lower weight than the edges of weight 3. So you won't see those edges of weight 3 in a single source min cut gadget. You'll just see the edge of weight 2 for all those four vertices in the left corner. And then, of course, for the vertex on the right corner, you will actually see the edge of weight 1 because that corresponds to the minimum cut. So if you take this and then sort of clump together vertices that reported the same single source min cut, then you get this kind of a partial tree. Right? All those four vertices in the top left corner, they get clumped into a single vertex. I don't really know what's going on inside that group, but I know all the other edges of my tree at this point.
How do you know these X relationships? Like you know S to that green block is 1.
Yes.
I mean, how do you know exactly? Imagine these green blocks are just a bunch of four vertices. How do you know they're connected in this way?
So this is in hindsight. So suppose your Gomory Hu tree looked like this. Okay, I'm saying that how much is being revealed by a single call to a single source min cut. Right? A call to Maxflow reveals just one edge. A call to the single source min cut problem reveals a lot of edges in this example. And then you can try and recurse inside the parts that didn't get revealed. So this seems like a promising approach because the depth of recursion perhaps is lower. It's revealing a lot of different edges. And in particular, that star example that I had, if you chose any particular vertex S, it actually reveals quite a few edges in one go. Okay, and for example, if you perturb the edges a little, it will reveal half the edges. Okay, good. So that seems to be good. However, it's not all good. So let's take the same Gomory Hu tree example, and let's say I chose my source to be the vertex on the right. Now, if I chose the vertex on the right as my source, then basically all the edges of the Gomory Hu tree are obscured by the fact that I have an edge of weight 1 there. Right? Because for every other vertex, its minimum cut to S is indeed that edge, weight 1 edge. Every other edge has higher weight, so I won't be able to see any of these. And so what I get is exactly my problematic situation, which is that I see just one edge, which I could have revealed with just an ST Maxwell. So it doesn't seem to be universally a good idea. In some situations, it seems a good idea, and depending on the choice of my source. In some situations, it seems to be a bad idea. Thankfully, Abood, Krauss-Grammar, and Debmalya showed that if you chose your source to be at random, then with some fairly good probability, this is instead of 0.1, you can choose your own constant, but with some constant probability, it's a good source in the sense that the recursive subproblems that you get, so these clumps of vertices that didn't get separated, those subproblems are small. They are a constant fraction smaller than what you started with. Yes.
Take this diagram. So I'm not fully clear. So you are running this single source min cut on the original graph.
Yes.
So running from S, you would know the shortest, the min cuts to all the vertices.
From S, yes.
From S. No. So what is that one?
So if your Gomory Hu tree looks like the tree I've drawn here,
But you have not constructed it yet.
we have it, then the minimum cut from S to every other vertex is the cut that separates S from every other vertex, because that's a cut of weight 1. Every other vertex also has that as its minimum weight cut, right? So that's the only cut all the vertices will report to you.
You would just know one. You would not know how it is.
Yeah, all this internal stuff will not be revealed. Other questions? Okay. Okay, so thankfully there was this lemma by AKT that shows that if you actually chose this source at random, then there's fairly good chance that your subproblems will be small, will be constant size smaller, constant fraction smaller. And that's good enough, right? Because I can just keep repeating a few times and one of these iterations will produce this property, will satisfy this property. Once it satisfies this property, then I know that I am down to some constant fraction, so I will only repeat log times. Okay? So that says that, in fact, I can use a single source min cut algorithm to solve the all pairs min cut problem. By the way, so for the students in the audience, this lemma is kind of something that you might try to prove on your own. This lemma has a very short proof, doesn't need you to know any Gomory trees or cuts or anything. It's just a lemma based on tournaments. So just try to prove this if you're interested. Okay. Theorem reduces the all pairs min cuts problem to the single source min cuts problem. Trouble of course is for the parts. Shortest parts, not that important. So problem, of course, is that we didn't have any algorithms for single source min cuts. The only algorithm that we know of or knew of is the completely naive algorithm where you iterate over all the vertices, all the terminals, and find ST max min cuts using Maxwell. Okay, so that's just an n-1 Maxwell algorithm and the completely naive algorithm for this problem. Okay, so but the rest of the talk we'll try to develop a better algorithm for single source min cuts. Okay, so that's our sort of new result restated. For single source min cuts, we now have an n-squared time algorithm. Now this algorithm is going to be an iterative algorithm with the following structure. So so we have a fixed source S, right? This is given to us. That's the source for which I'm trying to find min cuts. Now let me initialize the set of terminals. I'll call a set of vertices terminals, and this set will keep changing during the algorithm. So initialize the set of terminals to all vertices of the class. And the thing to keep in mind is terminals basically would be the set of all vertices for which I haven't yet identified a min cut from S. So initially I haven't identified min cuts for any vertex. So initially it's all vertices. Okay. Now, one other concept that will be useful for us is what's known as Steiner connectivity. So what's Steiner connectivity? This is the min cut or the min cut value with terminals on both sides. Okay, so among all the cuts that have at least one terminal on each side, this is the smallest one. So initially, the Steiner connectivity is just the global connectivity of the graph because everything is a terminal. So every cut has at least one terminal on both sides. So Steiner connectivity is just the smallest cut in the graph. But over time, as this set of terminals keeps decreasing, right, as this set becomes smaller, the Steiner connectivity keeps going up. Okay, so that's the picture you should keep in mind. The set started with every vertex. Steiner connectivity is just global min cut. Now it's squeezing down, fewer and fewer vertices. Steiner connectivity keeps going up. The extreme case is it's down to just two vertices. There are just two terminals. Then Steiner connectivity is just the ST min cut. So it's this sort of transition from a large set of terminals to small set of terminals. So let's say the Steiner connectivity at any given time, be lambda. In one of the iterations of this process is lambda. So in that particular iteration, what I'm going to be interested in is finding connectivity, the value of a min cut for all terminals whose min cut values are between lambda and 1.1 times lambda. 1.1 is just some constant larger than 1. It's not particularly important what constant, but some small constant larger than 1. I wouldn't care about all these vertices that are very highly connected to the source. Those will come later. For now, I'm only interested in those vertices that define Steiner connectivity, the terminals, and things that are close to it, things that have connectivity that's maybe slightly higher than that. Okay, these are the only ones I'll focus on in this equation. Now, if I'm able to find min cuts for all of these vertices, then I throw them out of my terminal set. Remember, terminals are vertices I haven't found min cuts. So I throw them out. But once I throw them out, everything else has a larger connectivity with the source that I started with. Right? That's why I didn't find those min cuts yet. Which means my Steiner connectivity now goes up to 1.1 lambda or higher. And then I will repeat the process. So given that all weights are polynomial, clearly this process will only repeat log times. Because in every step, the Steiner connectivity, this quantity is going up by a constant factor larger than 1. So it will only go up log n times and it will hit the maximum polynomial, whatever maximum connectivity you have. So this is the overall plan. Okay? Yes.
So lambda you're defining is like the min cut across all cuts that separate T.
Yes.
What guarantee do I have that any ST cut has? Like,
I mean, it's equivalently the minimum among ST min cuts for all the T in the terminal set. Right? Because it has at least one terminal on the opposite side of S. So that I will have that. Yes.
Identifying the terminals to satisfy this property without actually computing the value of lambda.
So I will guarantee through my algorithm that every vertex whose connectivity is between lambda and 1.1 lambda reports some min cut in this step. And then I'll remove those from my terminals.
Is part of terminals.
S is, let's say, always part of terminals.
Then you're excluding lambda or whatever it is.
So, I mean, S is this fixed source. There's no notion of an SS min cut. I mean, S has S is always in the set of terminals. Yes.
so the naive way of doing this would be to find, like, look at the subgraph induced by T, find a min cut, keep the side, throw away everything that's on the opposite side of this.
No, so subgraph induced by T might have a very different connectivity structure than the whole graph. Because all paths from S to those vertices can go through some external vertex. So you have to work with the whole graph. It's only the set of terminals that's changing, not the graph. Other questions? Okay. And in fact, I'll cheat even further, and I won't even do this for all terminals for this property. I'll just do it for a constant fraction of these terminals. That's all right, because if I repeat this log times, then I'll actually get rid of all these terminals, and then I can. Okay. So that's our goal. So our goal is to find these things that I'm calling single source Steiner cuts. So we are given a set of terminals T with some Steiner connectivity lambda and source S, and we want to find minimum cuts from S to all terminals T, to actually a constant fraction of terminals T, satisfying the property that lambda of ST is less than 1.1 times lambda. And of course, it has to be at least lambda, because lambda is the minimum value of lambda S among all terminals. Okay, so let me call these ST min cuts, the ones I'm after, the ones I want to find. Let me call these critical. I want to find these critical. Questions about this? The rest of the talk will just give an algorithm for this problem. Okay. So let me give you an example. So let's say at some point of time, these vertices in bold, those are your terminals. Vertices that are not colored, those are not terminals. S, as I said, is always a terminal. And I have three other terminals, T1, T2, and T3. And let's say the cut that separates S from T3, that's the one that defines Steiner connectivity. So the connectivity of T3, lambda of ST3 is actually 10. And the Steiner connectivity is also 10. Now, suppose T1's connectivity from S is 11, and T2's connectivity from S is 15. So in that case, I'm after these vertices T1 and T3 in this step. I am ignoring T2 for now. And T2 will come later once my lambda increases. And that's how the algorithm is. Now, in order to solve this problem, we are going to use something called a Steiner tree. So what's a Steiner tree? A Steiner tree is basically any tree of the graph, that's a subgraph, that spans all the terminals. So it's a tree that should include all the terminals, need not include non-terminals. Okay, so here, for example, I've seen a bunch of different Steiner trees. Now, for the purpose of, for intuitive purposes, what we are going to construct is a collection of edge disjoint Steiner trees. Yeah, and this comes with a few caveats which I'll mention in the next slide. But for now, imagine that I'm constructing edge disjoint Steiner trees, and all of these are spanning all the terminals. We'll call these things Steiner trees. Now, the first question is how many such Steiner trees can I construct? Now, I claim that you cannot actually construct more than lambda. Okay, why? Because remember, there's some terminal whose connectivity from S is lambda. So that means that the total number of disjoint paths that vertex has from S is lambda. And I'm using an unweighted analogy here. You can extend all of these to weight. But in unweighted graphs, let's say T2 was the vertex that had connectivity lambda. That means that in the graph, there are only lambda edge disjoint paths from S to T2. And each of these trees is consuming one such path. So clearly, you will exhaust all those paths after you have built lambda trees. You won't be able to build the lambda plus first tree. Now, what's not so clear is why should I be able to build lambda trees in the first place, right? Lambda is an upper bound clearly, but maybe you cannot actually get to lambda trees. And indeed, you cannot. But for now, let's imagine that you can. That will make our life easier, and then we'll come back and address this issue. So let's say you're able to construct lambda edge disjoint Steiner trees. Yes, so Nash-Williams cuts is Nash-Williams theorem is a special case of this, where terminals are all vertices and you talk about Steiner trees. Any other questions? Okay, so suppose I'm able to construct lambda trees. Now what can I do with this? Let me choose a random tree out of these lambda trees. Okay, R is a randomly chosen guide tree. What property does this tree have? So if you look at a critical cut, over these lambda trees, a critical cut has only 1.1 times lambda edges, right? The critical cut is something that's between lambda edges and 1.1 times lambda edges. Again, I'm using unweighted graphs because it's easier to explain. Everything also works for weighted graphs. So if you have between lambda and 1.1 lambda edges, and I choose a random tree, then in expectation, you don't have more than 1.1 edges, right, in the tree. Because all these 1.1 edges, sorry, 1.1 times lambda edges are distributed across these lambda trees. These trees are edge disjoint. So if I chose a random tree, in expectation, I will see at most 1.1 edges from a critical cut in that tree. And of course, every critical cut also has at least one edge. Because remember, a critical cut is an ST cut for some T. And that terminal T is in the tree. So the cut must be spanned by the tree. So you have this really tight concentration that if I take a random tree, I will deterministically see at least one edge from every critical cut, and I expect to see no more than 1.1 edges from every critical cut. Now, how do we use this fact? So we can take this expectation bound and turn it using like standard averaging Markov type analysis to a probability bound. Right? We can say that with constant probability, a constant fraction of critical cuts will have at most a constant number of edges in my tree. And again, this is just a standard use of like Markov bound type arguments. And this is going to be our useful property. That if I chose a random tree, a random guide tree, then a constant fraction of the critical cuts will only have a constant number of edges in this tree. And these critical cuts are the ones I'm really going to be after. I will try to find these critical cuts. And we say that such a critical cut, k respects the guide tree for some constant value k. It's not particularly important what constant the k equals 5. Okay. Now, as I said, there are a bunch of caveats on what I'm saying in this slide. Not essentially all of the things that I said are precisely not correct. So, for example, we cannot construct lambda as Einstein trees. For instance, because of the Maxwell theorem. So, if you think of a cycle and all your vertices are terminals, you can't fit in two spanning trees there. You can only draw one spanning tree. Right? But we can construct a constant fraction of that. Okay, and nothing really changes. If you instead of lambda, if you construct lambda over 4 trees, nothing really changes other than the value of k goes up by a factor of 4. So that's the first caveat. So that's existential. There doesn't even exist lambda existential standard trees. The next caveat is algorithmic. So we do not know how to efficiently construct these trees. Okay, so I mean, eventually I need to give an algorithm to construct the trees. We don't know how to do that very efficiently. But what I'm able to do is instead of edge disjointness, I'm able to ensure constant congestion. So an edge will appear in multiple trees, but only constant number of times. And nothing changes because of that. Okay, again, the constant in k, that changes, but that's okay. We can deal with that constant. And finally, for some technical reasons, these trees won't even span all the terminals. Okay? The crucial property will be that even when it's not spanning all the terminals, it will still have at least one edge in every critical cut. And that's all I needed from this spanning property. I needed these trees to be spanning the terminals because I wanted to say that in each tree, you have one edge from your critical cut. That property directly we will ensure, but we won't be able to ensure that these are spanning trees. Like these are spanning trees even over the terminals. Okay? So these are caveats. If the caveats seem confusing, just ignore them. Like those are finer details. The more important thing is what do I do with this tree? Now I've chosen this random tree. I know that there are a bunch of critical cuts. These are ST min cuts for some keys. And I know that each of them, let's say, has 5 edges, at most 5 edges in my tree. Now, how do I find those cuts? That's what I'm going to talk about. Okay, so at a high level, let's step back. There are 2 questions now. The first is how do I build these guide trees? I need to first be able to build these to be able to randomly choose one. This I'm not going to be talking about at all. But this is where we lose a factor of n squared. So this algorithm uses multiplicative weights update along with some other techniques. If you are interested, I encourage you to look up the paper. I'm happy to discuss offline, but I'm not going to be talking about this in the. What I'm going to be showing you is what we do with a tree. Once I have constructed these trees and chosen a random tree, how do I find these critical cuts that k respect this tree? Again, think of k as being 5, some constant. Okay? Questions?
One place scale one to become 45.
Yes, I mean it's Monte Carlo in many places because in that constant fraction that I said, the fact that you get all of them is also. Okay. So how does a guide tree look? It looks somewhat like this. So there's this vertex S, which is the source. There are terminals, let's say T1, T2, and T3. And then there are these critical cuts. I've colored the critical cuts by the terminal. So let's say the critical cut for T1 has those red edges in the tree. Critical cut for T2 has the green edge. Critical cut for T3 has the purple edge. These need not be disjoint. The same edge can act as an edge in a critical cut for 2 different terminals. But this is what we are given. Okay, and we are trying to identify the cuts. Now, one important thing to note is that, let's say when we are trying to find the ST2 min cut, it's not sufficient to just identify the green edge in the tree because the tree is non-spanning. Tree doesn't have all vertices. So even if I identify the green edge, that just tells me that the vertices on the tree are partitioned in a particular manner in the cut. What's going on with the vertices outside the tree? We don't know. So something needs to be happening on the graph itself. I need to find the cuts on the graph. The tree itself doesn't have enough information. Okay, so the tree is a guide to what I can do on the graph. but eventually I have to run something on the graph to be able to find my critical cuts. Okay, so I'm not going to go over the details of this algorithm anyway, I'm well over time, but I'm going to show you maybe one nugget of how this problem is eventually solved. So let's take this tree and let's take the centroid of the tree. Yes, it's technically the centroid only considering the terminals, but just think of the centroid, some central vertex of the tree. Now you take the centroid and root the tree at that centroid. Let me call that centroid R. The source S is somewhere deep down. It could be R, but it could be some other vertex as well. Now let's look at now there are a bunch of different cases depending on where the critical edges are. Remember, there are at most 5 edges for a critical cut in this tree. Depending on where those edges are, you have 2 or 3 different cases. Let me look at just one case in this one. So let me look at the case where the edges are all in the same subtree of the root. Okay, so here I have shown 2 situations that where this happens. In one situation, the edges are in the subtree containing S. In the other situation, the edges are in a subtree containing the terminal T prime for which the red edges define the critical cut. Okay. So what do we want to do really? So let's, for a second, let's forget about all other terminals, and I want to find the SK min cut. How should we go about doing this? Well, one natural idea is to say that, well, let's take the picture on the left. My critical edges are in the subtree containing S. So what is the rest of the stuff doing? That's not giving me any information. All of that is on the same side of the cut. So why don't I contract off everything except this one subtree? This subtree contains the important information, the critical edges. All the rest is junk. That information is not useful to me. So let me just contract all of them. And that in general seems a good idea because remember, I rooted my tree at the centroid. So that means that if I contract all except one subtree, I'll lose at least half of my terminals. So I'm making progress. I'm losing half the terminals. So the depth of recursion is actually great. So if I contract it and then recurse, the depth of recursion is just log n. Because every time I'm losing half the terminals. The problem is with the width of the recursion. You might have a lot of different subtrees. For each of those subtrees, you are making this contraction and then going back and running your algorithm on the same graph. Right? So if you had, let's say, a polynomial number of subtrees, even in just one layer of recursion, you're done. Because you have the same graph showing up in all these branches of your recursion. And the crucial thing to observe is that all this operation of contracting stuff is happening on the tree, not on the graph. If it was happening on the graph, maybe we have some savings. Because then parts of the graph are getting contracted, each individual subproblem is only working on some part of the graph. But if we are doing this on the tree, I'm still passing the entire graph to all my subproblems. So that's very slow. So we somehow want to do this on the graph rather than the tree. So let's say the ST prime min cut, the cut I'm after, looks like that in the graph. It looks like that blue cut. Think of the min cut that separates all the terminals in this subtree from S. Okay, so all the terminals in the subtree. So that looks like some cut, orange cut. Now, because of some standard properties called uncrossing, the intersection must also actually be an ST prime min cut. So that says that if I contracted my graph everywhere outside this orange cut, I wouldn't lose information. I would still be able to identify an ST prime min cut, a critical cut. Okay, so that's what we do. We simply identify for every subtree the minimum cut for all the terminals in the subtree of the graph. And then in each subproblem, we contract off everything except just one of these orange pieces. And that's good because now the graph is being contracted. So the sum of all these subproblems, even if the width is large, sum of all these subproblems is just one copy of your graph. Okay, so that kind of reduces the problem to this question of how do I find these min cuts? This is a lot of different min cuts. How do I find that efficiently? And for that, we use something called an isolating cut. So I think I'll skip this. This is something I worked with Jason Lee on. So we in a different context. And Abod Kraktower and Tribbles also discovered it in a different context. But there is a gadget that can actually solve this problem of taking splitting up your terminals into groups, and then finding min cuts for each group, separating it from the rest of the group. Okay, so let me actually skip isolating cuts. Let me get to this. So once you run isolating cuts, that actually solves the problem. You can recurse after that. And let me just go over the steps, because we did a lot of reductions and kept simplifying the problem, and I'm sure I lost you at the end because then it became really heavy. But let me go over the steps of the algorithm. So we construct a Gomory tree and then square time, and this is what we do. We first use a recursive algorithm that reduces the problem to single source min cuts. Okay? So all pairs min cuts has now reduced to single source. Next, for single source min cuts, we actually use an iterative algorithm that reduces it from a single source min cuts to only finding near Steiner min cuts. Right? Steiner min cut being lambda, it finds all min cuts between lambda and 1.1 lambda. How do we do that? We construct this maximal packing of guide trees, which are really just like Steiner trees. Do that in n square time. We choose a random guide tree. On the random guide tree, we reduce the problem further to finding a constant fraction of critical cuts that k respect this guide tree, where k respect is for some k that's constant, let's say 5. And finally, we use a bunch of techniques and some case analysis, techniques like isolating cuts and cut thresholds, which we kind of discovered in other contexts, to find these critical cuts in polynomial pairs. So that's the whole algorithm. Let me end with this slide. So I don't need to repeat the result, but one interesting question that also came up earlier is whether the running time can be improved and made the same as Maxwell. Right? We are still incurring n squared. Can we make that almost linear time? So we have some results. So I think we can now do this, but that needs a set of different techniques. And the main bottleneck in the algorithm I presented was this n square time process to construct the guide trees. Once you have constructed the guide trees, the rest of the algorithm, the one I kind of presented with two more details, that actually takes almost linear time. The first part takes n square time. So that part we can optimize using techniques from dynamic algorithm. That's all I have. Thank you. Yes.
For centroid finding, what is the best known algorithm?
Oh, the linear time algorithm. Centroid on a tree, but weighted centroid.
It's two pairs.
Yeah.
If you're interested in the top case.
Yeah. So there is an algorithm. So there is a problem called it's called weak Gomory and Hu tree, which says that if I take the Gomory and Hu tree and contract all the edges that are larger than a certain threshold, how fast can I construct this on a partial thing that only reveals like the low weights? And that, like even in that old paper that I had with permeation, that we actually solved faster. So that can be done much faster.
It's not mentioned that there are only n-1 possible values.
Yes.
So if you want only n-1 cuts, which satisfy that, let's say we're interested only in those.
Yeah.
But one per each value.
Yeah.
Is there a way?
Well, I mean, this Gomory tree actually is identifying n-1 cuts. It's not actually identifying n-2 cuts. Identifying n-1 cuts, but then showing that those n-1 cuts actually are min cuts for all n-2 pairs. So many pairs will have the same cut.
Balance
No. So balance separator means that you take a graph and you split it into, so you find a cut such that each side of the cut has at least some multiplication of it. Centroid is on a tree here, not on a graph, and it just means that each subtree will have some less than a multiplication of it.
on a tree, they will be
Well, I mean, balance separator, usually we talk of balance separator as a bipartite separator. Here, a tree can have very high degree. Yes.
So,
Gomory and Hu's algorithm was doing this, right? The other ones, unweighted graph, etc., were not here.
I mean, what is the ones using ordinary methods?
Oh yeah, the order and Maxwell, the Gomory and Hu algorithm was. But everything after, like that's 1961 algorithm was created. Everything after that eventually was. So deterministic, even much easier problems are difficult, like seem to be. Like, for example, just take the graph and partition into components that are taken. Even that is. Other questions?